This should be the last screencast for Chapter 16. Picking up where we left off, you might recall that an equilibrium constant expression is something that we have invented as scientists to talk about equilibrium reactions. And by definition, by choice, we define that constant as being the molarity of each product multiplied together, divided by the molarity of each reactant multiplied together, where each of those molarities is raised to an exponent that is the same as the coefficient in the balanced equation. Unlike in kinetics, where the exponent has to be determined by experiment and does not automatically follow from the stoichiometry of the balanced equation, in equilibrium expressions, because they're not reflections of reality, but reflections of something we have created, that I mean by that physical reality, therefore the exponents can be defined any way we want, and we define it as being the exact coefficients from the balanced equation. And so picking up where we left off, there are some interesting situations. The first example is going to be this. If we have a reaction involving carbon plus oxygen to produce carbon monoxide, hopefully this reaction is not a very common one, because there certainly is a lot of solid carbon or coal, or for that matter, graphite and diamond around, and it's exposed to oxygen, and you would hate it if you're making carbon monoxide all over the place. Obviously, in terms of entropy, where you have 1.5 moles of gases becoming 1 mole of gas, that's an increase in order or a decrease in entropy, and that generally is not thermodynamically favorable. Plus, we would need to know the temperature at which this becomes possible, which I would imagine is very high. So you'll notice we have a fraction in our balanced equation. If we set up the equilibrium expression, it's as you expected, and we have a fraction for oxygen in the denominator. That fraction of 1/2, of course, means to take the square root. And we get a value of 4.6 times 10 to the 23rd, which implies that at the right temperature, in the right conditions, this is actually a favorable reaction. Now, what if we don't want, for whatever reason, to have fractions as coefficients in the balanced equation? So we double that. The 1 becomes a 2, the 1/2 becomes a 1, the 1 becomes a 2. And we set up our equilibrium expression as always. And if we had the right data, we would be able to find that the constant has a value of 2.1 times 10 to the minus 47 compared to 4.6 times 10 to the 23rd. Now, if you inspect these numbers a little bit, you would recognize that this number right here, when you square it, actually gives you this number right here. And so the rule is anytime you double the coefficients in a balanced equation, you're going to have to square the equilibrium constant. The reverse, of course, would also be this true in that if you were to cut all of the coefficients in half, you would take the square root of k in order to find the new value of k when you cut all the coefficients in half. And we could say the same thing if you were to multiply all of your coefficients by 3, then your first k value would be cubed to get the new one, and then over here, of course, if you're going the other way, it would be the cubed root. So that leads us to our first conclusion. When the stoichiometric coefficients of a balanced equation are multiplied by some factor, usually it's a 2, could be a 1/2, the equilibrium constant for the new equation is the old equilibrium constant raised to the power of that multiplication factor. Now let's look at another example. Let's suppose we have this reaction right here, and we set up our equilibrium constant expression by putting our products in the numerator, and the reactant goes in the denominator. All the coefficients are 1, so all of our exponents are 1, and we find the value. Now let's suppose we wonder about the reverse reaction. Now, before we do the reverse reaction, you'll notice that this is a -4 for my exponent, which means this reaction is reactant favored. It does not want to go to the right very much, which is why the numerator is so small compared to the denominator. That would imply that if we reverse the reaction, we should have a reaction that does want to go to the right when we reverse it, because going to the right when we reverse it is the same thing as going to the left when it's not reversed. And sure enough, when we set up the equation this way, look at the equilibrium expression, find the value of K, you'll notice that the new value of K is the reciprocal of the previous one, the reciprocal. And that's how we managed to get a positive 10 to the third as opposed to the 10 to the -4th. So that leads us to our second conclusion. The equilibrium constants for a reaction and its reverse reaction are reciprocals of one another. Now let's do a third example, special situation involving equilibrium constants and their expressions. And let's say we're going to be adding a couple of equations together. For example, here we have one equation which involves silver chloride dissolving in water to the little extent that it does, and a second equation involving these silver ions that were just produced complexing with ammonia to make this complex right there. You'll notice that in the first reaction, as we might expect, since silver chloride is so insoluble, we have a very, very small equilibrium constant, 1.8 times 10 to the -10th. However, every single time we do produce a silver ion in step 1, that silver ion immediately complexes with available ammonia because we have a 1.1 times 10 million. And so even though this first reaction up here, the first reaction, is not a likely reaction, it's going to and does not want to go to the right, it's going to continue to go to right because we keep taking these silver ions out of the solution and complexing them with ammonia. So if we wanted to look at what is the overall net reaction, we need to add these two reactions together. Now, in order to do that, we'll come over here. It turns out that when you add two reactions together, you multiply their equilibrium constant values. And so you can see that what is very, very unlikely, I'm sorry about that, this thing keeps erasing stuff, what is not so very common becomes a whole lot more common, and because we've multiplied these two equations. So we've gone from 1.8 10 millionth, I'm sorry, that would be 10 billionth, and now we're down to the thousandth. So it's much more likely for this reaction to go to the right, not compared to originally. And you multiply the two values of K together, as it says here. If I had three equations, I'd multiply three equilibrium constants together, and so forth. So our third conclusion here is that when two or more equations are added to produce a net equation, you might recall we used to do that with Hess's law, the equilibrium constant for the net equation is the product, meaning we multiply them together to get the new the net equilibrium constant value. And here you have a couple of examples. If we look at equation number 1 right here and equation number 2 right here, you'll notice immediately that equation 1 has been divided in half to get equation 2. So since we're dividing in half, we need to take the square root of 3.5 times 10 to the 8th to get the new value. And when we look at equations 1 and 3 on this side, when we're coming from this equation down to here, equation 3 is the reverse of equation number 1, and so we're going to take the reciprocal, which is what that says right there. And They actually do the math for you right there. That's not very difficult. All right, disturbing equilibrium. Here's where we pick up with Le Chatelier's principle. Remember, Le Chatelier's principle applies to both physical and chemical systems at equilibrium. Right now, we're looking at being in chemical equilibrium, not physical equilibrium, like when you might have ice in water or water vapor trapped in a container above a solvent, above water. So the equilibrium between reactants and products may be disturbed in 3 ways, and we're going to look at each of these 3 ways on the next page. And those 3 ways, by the way, are summarized in this chart. So as long as we're looking at the chart, we're going to focus on this. You can come back to this later. You'll notice that here's what happens when you have the addition or the removal of a reactant, or the addition or removal of product. Then we have the idea of decreasing or increasing volume and pressure, which only is going to affect gases. We don't worry about it with liquids and solids, obviously. And then in number 3 is when you increase or decrease the temperature of the system at equilibrium. And here, something that's very important, test question. The only thing that affects the equilibrium constant is going to be when you change the temperature. It turns out that when you change the quantity of reactant or product either way, or change the pressure or volume of a system at equilibrium that involves a gas, it actually does not change the value of K. So let's go ahead and apply Le Chatelier's principle, and let's remind ourselves of what that is. A change in any of the factors that determine the equilibrium conditions of a system will cause the system to change in a manner to reduce or counteract or countermand or to partially offset the effect of the change. Remember, it doesn't completely get rid of that change. It just partially compensates for it. Excuse me. I use an example. It doesn't turn out nicely in the end, but the example is, what if your grandma moves into your house, whereas before you had your nice routines all down, who uses the bathroom when, who has which part of the refrigerator perhaps, who needs to be available to who gets to use the car at different times, who's got the different chores and all of that, and you have this nice equilibrium. And then your grandma moves in, takes over one of the bedrooms, takes over part of the fridge, has various appointments, to get her hair done or go to the doctor, and all of your equilibrium situations change. Now, all that compensation does not take you back to an original condition that involves no grandma. That would not be nice if you were to somehow figure out a way to get rid of grandma. You hate it when that happens, I hope. But you have to adjust, and you reach a new equilibrium that's different from the original conditions. So, what happens if you add or remove a reactant or product? And we've done this before in physical changes at equilibrium, but your reaction is going to go to partially offset what's been done. For example, if we increase this product, the reaction is going to go to the right to try to decrease it. Or, and I will erase that, what if we decrease my reactant? Then the reactant is going to go to the left in order to increase some of that reactant. And let's pause on this one just for a minute, so that if my molarity of butane goes down, and I'm going to write my expression right here, and I've got my iso up here, and I've got the butane down here. So if my concentration of butane goes down, the reaction is going to go to the left to increase some of that butane. So when it's going to the left, the iso is going to go down, but it's going to add some butane, and the net change, if we add these two vectors together, we get a smaller arrow down that matches the smaller arrow down up there. And that's why the value of K does not change. Then, of course, we can erase this, and this, and this. And we can say, okay, what if we increase my concentration of isobutane? Then the reaction is going to go to the left to take some of it away. So if isobutane goes up, the reaction is going to go to the left, which is going to increase some of the butane. But in the process of increasing some of the butane, it's going to decrease some of that isobutane that you added, and your net vector there is the same as that. The value of K does not change. And here's an example problem where we have butane and isobutane in equilibrium. And normally they specify the temperature. You'll notice that we have a 1 liter flask, so we don't have to make any adjustments if I had like a half-liter flask or a 2-liter flask in order to calculate my molarities. And when we go to look to see what we're given in this problem, we are given the initial molarity, and we are also given a, let's see, the initial molarity is right there. That's of isobutane, and we're given the, of butane, we're also given the initial molarity of the isobutane, we're given that. And then we are told we are adding 1.5 moles of butane to this 1 liter flask. And that's what you're given right there. So I would think of this whole thing right here as being my initial. We have the pre-initial with this and this. Then we add this much, and now we have our starting place. And so 0.5 plus 1.5 is going to give me 2.0 here. And so when the reaction goes to equilibrium, it's going to go to the right because we're adding butane. And so we're going to have a plus X and a minus X. And here's my 2.0 minus X when we finish the calculation. And we have 1.25 plus X over here. And then when we go to write our equilibrium expression, this comes down there, and this comes down there. And now when we can solve this equation for X, and then we can plug it back in there, and plug it back in there to get the molarities that are now at equilibrium. And some books will use a graph like this that basically says any place along this line, you're going to be at equilibrium in terms of your molarity of isobutane compared to your molarity of butane. You have many places that you can be at equilibrium. And so if we were to add 1.5 moles of butane like we did in the previous problem, equilibrium shifts, but instead of going back this way, which it doesn't do, it ends up back there. And you end up at equilibrium at different molarities, but the same value of K nonetheless. What about the effect of volume changes? This can happen in two ways. While you can change the volume of the container, but you can also change the pressure. I don't mean you can change the volume in two ways, other than making the volume smaller or making the volume bigger, like in a cylinder with a piston or like in a syringe. But you can also change the concentration of the gases by increasing or decreasing pressure. And again, if any increase in one is going to force the reaction to go towards the other side and vice versa. It's not going to affect the value of K. And one of the things you need to keep in mind is in this particular reaction, I'm going to erase the green marks. What I want you to focus on is we've got 2 moles here and 1 mole there in the stoichiometry of the equation. So if I increase the pressure, which way will the reaction shift in order to offset some of that pressure? Well, by two particles becoming one, by going to the right, you can reduce the pressure. So an increase in pressure is going to force the reaction to the right. By the same token, if you had a decrease in pressure, how can this reaction compensate for that? Well, by going to the left, you can break down one particle into two particles, and now you have more particles banging against the inside of the container in which the gas is, and that will increase the pressure to offset the stress of reducing the pressure. And so here are some bullet points to wrap that up. You have the stress of a volume decrease, which is the same as increasing the pressure. And it'll move in the direction to reduce the number of gas molecules. Again, if you increase the volume, that's tantamount to a decrease in pressure, so the reaction will go in the direction in order to increase the number of particles. If you have the same number of moles on both sides, then volume change has no effect on equilibrium. And finally, number 3, what about the change in temperature? Remember, the change in temperature does cause a change in the value of K. And here it's critical that you know whether you have an endothermic or an exothermic reaction. In this case, I have a endothermic reaction, so this means that my heat is on this side of the equation. And now you just consider heat as if it's actually just a reactant, just like nitrogen gas and oxygen gas. And so if we were to increase the heat, the reaction would go to the right to take some of the heat away. And in the process of going to the right, it makes the nitrogen monoxide molarity go up, and the molarity of your two reactant gases go down, and now your value of K goes up because your numerator becomes bigger and your denominator becomes smaller. By the same token, if we were to cool this down, reduce the amount of heat, the reaction would go to the left to replenish some of that heat, and in the process, the numerator would go down, the denominators would go up, and your value of K would go up. By the same token, if you have an exothermic reaction, we would do the same thing. We would put the heat on this side of the reaction now, and any increase in temperature causes the reaction to go to the left, and if you're increasing the denominator and decreasing the numerator, your value of K is going to go down. And again, the reverse of that process would be true if you were to cool this reaction down, this exothermic reaction down. And here you have some pictures to try to illustrate that, as you have a color change from slightly brown, which represents a smaller concentration of nitrogen dioxide, to a darker brown, which would be a higher concentration of the nitrogen dioxide, depending upon the shift due to high temperature and low temperature. So we can conclude when the temperature of a system at equilibrium increases, goes up, the shift in the direction to absorb the energy, it'll go whatever direction that takes, and that will change the value of K. And the same with any decrease, and again, it changes the value of K. The last thing is an application of Le Chatelier's principle. And this is a lot of history behind this reaction. Books have been written about this history and about this reaction. It's got two people's name here, Fritz Haber, who came up with the ideas, and then Bosch, who kind of industrialized it. Fritz Haber, Nobel Prize winner in 1918, but in the beginning of World War I, he is also the father of maybe chemical weapons. And early on in World War I, 1915, I believe, in Ypres, Belgium, his release of chlorine gas into the trenches downwind where British soldiers were killed or incapacitated about 5,000 troops. And Germany did not capitalize on that success. I use that term in quotes. And which is a good thing because it took time to figure out how you're going to combat somebody that's using chemical weapons. Chemical weapons are used today. They're even used, I believe, in the country of Syria by their own king against one of the ethnic groups there. They've been used by other groups, sarin gas in a subway in Japan, I recall. So, and this is one of the areas that I studied during my summers in Idaho, was the detection of chemical weapons, at least the degradative products of the chemical weapons, what they turn into when they break down and end up on the surface of things. So anyway, the chemical weapons have nothing to do with this part of the story, but show you the tragedy and the irony of someone like Fritz Haber, who is considered the killer of thousands and the savior of millions, as you will figure out in a minute, and yet he gets a Nobel Prize. Obviously not for the chemical weapons, but because of this process here, which greatly ramped up the ability to produce nitrogen compounds, and the nitrogen compounds are what you need for fertilizer. By some estimates, upwards of half the population on the planet right now are beneficiaries of the Haber-Bosch process that can take nitrogen gas out of the air, and now I'm going to start using my pen again, and fix it so that it can become a nitrogen compound, which can be the precursor, the necessary ingredient for fertilizer, or the actual ingredient itself. If you drive past rural farm areas, sometimes you see barns that might have tanks of ammonia, which they use for fertilizer. Now, nitrogen gas, you'll recall, has that triple bond. It makes our atmosphere extraordinarily stable, and it's very, very, very difficult to break that nitrogen bond. And we want nitrogen, this nitrogen gas, which is in great abundance, 78-79% of our atmosphere. We want to fix it so that it's in the form of a nitrogen compound, like ammonia, or an ammonium compound, or nitrates, or nitrates. Now, it happens naturally in the ground because there are bacteria, especially around certain kinds of plants, that fix the nitrogen for us. They take the nitrogen out of the soil, and these nitrogen-fixing bacteria convert it into nitrogen compounds, which are absorbed by the roots of plants and then taken up into the plant and produces food. But now that we have the Bosch-Haber process, we don't have to rely on the relatively slow process and dispersed process of getting our nitrogen compounds from bacteria. We can mass produce this ammonia. It's one of the top 5 chemicals produced in the United States. It's also a precursor, by the way, for making explosives. And it kept Germany in World War II going because we cut off the supply of saltpeter, potassium nitrate, and Chile saltpeter from the country of Chile, sodium nitrate, and bat guano, or bat feces, from South America as well. We blockaded all of those shipments, and Germany had to rely on this process to produce the nitrogen compounds for making their explosives. In any case, it's estimated that 1/3 of your annual global food production uses ammonia. By the way, Fritz Haber's wife committed suicide back in 1915 because she was just distraught and argued with her husband over his role in all of this. In any case, how does this show the Le Chatelier's principle? In showing Le Chatelier's principle, this reaction is exothermic. So if we wanted to produce more ammonia, we would want this reaction to go to the right, which means we would want to cool the reaction down, make it very cold, so that the reaction would go to the right to replenish some of that heat, and in the process make ammonia. The problem is, the colder the reaction, the slower the reaction. Remember kinetics. That's another thing you have to take into consideration. The colder the reaction environment, the more slowly the particles collide together. So cooling it down is not going to work. In fact, it's going to be counterproductive. So what we're going to do then is we are going to increase the pressure, because notice that we have a 1 and a 1 for our coefficients over here. I'm sorry, that's not a 1. I missed it because of that circle. There it is, it's a 3. We have a 1 and a 3 for my coefficients. So we have a total of 4 moles on the left and 2 on the right. So if we can increase the pressure, the reaction will go in the direction to try to decrease the pressure. So we greatly increase the pressure in this container right here to force the reaction to go to the right. And that's very important. Another thing that we do is we add a catalyst. And they finally found a relatively cheap catalyst. All of these compounds are not terribly expensive. This is a form of rust, and silicon dioxide is basically sand. And we can force this reaction. The catalyst will speed up the reaction going to the right. Another thing that we do is we remove product. As we remove product and siphon it out all the time, the reaction can keep going to the right. So this is the application of Le Chatelier's principle to the Haber-Bosch ammonium production process. Now you notice that this does take an awful lot of energy. The energy is involved in producing hydrogen gas. That might involve electrolysis or chemical process. You also have to purify your ammonia because the atmosphere, even though it's 78, 79% nitrogen, has those other gases in it. That's expensive, and that takes energy. So it is estimated that this process consumes 1 to 2% of the global energy consumption, and that's a significant amount. And it's responsible for maybe 3% of the global carbon emissions, should that be a real concern. And it also involves using 3 to 5% of our natural gas in order to provide the energy to make this work. So this Haber-Bosch process is so important, it's often incorporated in some way or another on an AP chemistry test.